Îl voi invita acum pe scenă pe Lucian Cristea, care este software engineer la Bosch. El se ocupă de tehnici de procesare a imaginilor și algoritmi de deep learning și machine learning și astăzi ne va vorbi despre dezvoltarea de sisteme video pentru automated driving.
Salut tuturor! Mulțumesc pentru introducere. I will now continue in English because hopefully we have some guests which are from other countries as well. So I will say some words today about video systems development and the stuff that we work at Bosch. So I will start off with a quote from Wilhelm II, the Emperor of Germany, more than 100 years ago. He said that he believes in the horse, and he said that he does not believe that cars will become a reality. Now, obviously, we can look back and say how wrong you were, Mr. Wilhelm. But this is something that we say today. I believe in myself, and I don't believe that a machine will be able to replace me as a driver. Now, I hope that you notice the similarity. So like Mr. Wilhelm believed 100 years ago only in his horse and was wrong, we now believe only in ourselves. So we do not believe that autonomous cars may become reality. And this is, of course, wrong. I will now continue with some of the directions that we are going towards. So we have electrified driving. So you've probably noticed that most of the producers tend to replace combustion engines with electric cars because they are greener, let's say. We have the automated driving path, which is what I will talk about today. And then we have the connected drive path, in which we want cars to communicate with each other. And this part of connectivity is closely related to automated driving, because cars which are autonomous would like to also communicate with each other. So I will now continue with this automated part. Some of the activities that we have in Cluj include, of course, video systems development. So developing algorithms which are based on a camera, which is the purpose of this presentation, but we also have radar systems, so detection of depth or 3D environment. We have connectivity topics, ultrasonic systems, and last but not least, electric power systems, which my colleague Septimiu will continue in the next presentation. And you also see this central processing unit stuff. This means that we aim to have all of the computations done in a car performed in just one single location. This is because we want to have just one big computer inside the car, rather than have a lot of small computers placed in several locations, like at the camera, at the radar, and so on. So now I will first start with the levels of automation. So what does it mean to have an autonomous car? And the general understanding in the automotive car community, is that we have 5 levels. So we have level 0, which is, of course, no assistance. Then you have level 1, which means you can take your feet off, so the car may brake or accelerate on its own. Then you have hands-off, which means the car can also control the steering wheel, but the driver needs to pay constant attention because the system may not be good enough to handle all situations. Then you have level 3, which is eyes off. So the driver may, for a certain period of time, not look at the road, and the car is good enough to handle all conditions by itself. So you may look at the passenger, or you may look at something else, and the car will continue to drive. Then you have level 4, which is mind off. So you can ignore the fact that you are in a car and think of something totally different, and the car will, by itself, handle all situations. Then you have level 5, which means that there is absolutely no case in which the driver must intervene. There is no possible outcome in which the car determines it cannot cope with certain situations, and it will autonomously by itself drive. Now, where do we stand? Level 2 and level 3, we aim to have in production cars right now. So you can buy a production car which has a level 2 or level 3 automation level. Maybe level 3, not all cars, maybe in the next few years, but level 2 you can definitely buy now. And level 4 and 5 are mostly done for research. So we try to have cars which are, let's say, very autonomous, only done in research because it requires to have a lot of very complex sensors and very expensive sensors. And even with these, it's really difficult to make the car cope with absolutely any situations. You must imagine that an autonomous car must handle everything that a human driver can handle. And now, if someone says, we are at level 5, I mean, someone says they have a car which they can put anywhere and under any conditions, and it will work, I will say, bring it to Romania. Let's see how it copes with holes in the road, no lane markings, no road signs, maybe aggressive drivers, maybe drunk drivers, and so on. So some of the functions which you see here are what we develop for production cars. The ones on the left assist the driver, so it helps the driver brake or perform a steering maneuver to avoid something. In the middle, you see partially automated, so it can, in certain situations, drive the car on the motorway or drive the car in a traffic jam, while the stuff on the right is aimed to be a level 3 system, so the driver can actually not look at the road and the car will be able by itself to drive on the highway or drive in a traffic jam. So how does automated driving work? So you first have to sense. So the car is like a human. It first has to sense its environment, to determine what it sees. Yeah? Then it has to think. Okay, I see some pedestrians, I see some cars. What do I have to do? So it has to think. And then it has to act. Yeah? So it has to give commands to the steering and accelerating brake commands. Yeah? This last part will be detailed by my colleague Septimio. I will do. This is not, I didn't, yeah. Okay. Now I will move on to the first part, so the sensing part. So what kind of sensors can we put into a production car right now? So what's really feasible? So we can have long-range sensors like a radar, which can go to hundreds of meters, so detect cars which are further away. We have mid-range sensors and close-range sensors like a ultrasonic, which is usually used for parking assist. Then we also have the camera, which is the purpose of this presentation. And now, what can you do with the camera, or what do you want to do with the camera? You want to extract meaningful information from the road. This means you want to detect, of course, cars, but not only cars, but pedestrians, and other meta-information such as traffic signs, which show you where you can go or with what speed you can go. You want to maybe determine also the weather state, the pavement state, so whether it's wet or not. You want to maybe localize yourself, know on which lane you are or in which city you are on, and things like this. But the most challenging part is to determine the free space, so the space in which the car can go to without hitting anything, and objects on the road. So these are some examples here. So you can see here some lane detection. So it detects the lane markings. You can see here we can detect objects such as cars or pedestrians. We can detect the car's lights, front lights or back lights. And we can also detect traffic signs. Yeah? This is all done by means of a single camera, so without any other stuff, just one single camera. This is usually done by means of either classical computer vision algorithms or machine learning. And now there is some big advancement which I have omitted on this slide, and I'm sure most of you know about. And this is, of course, deep learning. So in latest year, deep learning has become very, very popular because we now have a lot of processing power. So now the limitations of a mono video system, the limitations would be that we cannot, it's very challenging to determine the depth from such a camera. And we try to determine the depth of objects by using a radar or by doing a process called 3D reconstruction. Now let's see some of the algorithms that we use. Now this first 3D reconstruction, what does it mean to do this 3D reconstruction? Now to very easily understand this, I would like the audience to try what I say. So you can put a finger in front of your eyes, yeah? And then close one of your eyes, and then close the other, yeah? And you will see that the finger goes like this, yeah? This means that with one of your eyes, you see the finger more to the left, while with the other eye, you see your finger more to the right. And you see that there's a shift between them. Now, if you put your finger further away and you do the same thing, you will notice that the shift is smaller. Now, this means that if we have a stereo camera, which means two cameras, like we have two eyes, the depth of the object is directly correlated with how much shift there is between the two images. Yeah? So objects which are close will have a big shift, like you saw with your finger, while objects which are further away have a small shift. And based on this, we can extract actual depth of each point in the image. So this means that we can have a 3D representation of the environment around the car. And the image which you see here on the right, this pointer doesn't really work, but you can understand, shows the depth of each point, and it's color-coded, meaning that stuff which is close to yellow is close to us. Stuff which is close to black or blue is further away. And you can identify that we have a car here on the left, yeah? And in the background, everything is more further away. And so this is a way of constructing the environment around us. Now, maybe we want to achieve the same thing, but with just one single camera. So like we are a pirate, so we do not see with one of our eyes. Now this is more complicated because now you don't have two separate images at the same point in time. You have two separate images at different points in time. Yeah? So it's like I look at my finger like this, and then I move a bit closer and look at it again. Now this has higher errors because the camera moves between the two frames, and the objects move between the two frames. And it's very difficult to estimate how the camera moved and how the object moved. Yeah? So it's a bit more challenging, but it's not impossible, and it's something that we actually do. Now I will do a case study so that you understand how we go about building things. So let's say we want to detect what I said was one of the most important things, so detect the drivable space. Detect where the car can go through without hitting objects and without going off the road, because it's something we do not want to happen. So we have some situations here, like you see, maybe in town, maybe a road with dirt, maybe with snow, maybe with grass. Remember, an autonomous car should handle all situations. So how can we do this? Yeah, this you see colored with blue, what we would like to have. Yeah, so the drivable space. So how do we go about doing this? So we could try to detect the lane markings. Yeah, and we could reason the fact that the drivable space is between the lane markings. Yeah, and you can see in the picture in the left, we have detected the lane markings, and we can say that the free space is inside it. Yeah? Now, what's the main problem with this? What happens if we have no lane markings, like we have in a lot of cases in Romania and in a lot of countries, other countries as well? Well, something bad happens. We cannot detect anything. So it's not enough to have a system which does only this. You can see here again some examples where it does work. So in town, or maybe if you are on a highway and you see a curve, it does work. But the problem is, if we don't have lane markings, it doesn't work. So then let's try another method. This semantic segmentation. So this is done by means of deep learning. So I think most of you are familiar. So we use a neural network which is inspired from the biological neural network, so what we have in our brains. And we use it to segment the image into different classes. So we can have a class with red, as you see there, which represents the road. with blue represent the cars, maybe with pink represent the sidewalk, and with yellow, I think you can see somewhere in the distance, there you can see some pedestrians. Yeah? So this is very helpful because it helps us understand what's in the scene in front of us. So it can not only detect the road, but it can also detect other objects on it. Yeah? And because, so to have good performance with such a system, you need to have a big data set. So fortunately at Bosch, we have a lot of cars which drive around the world and gather information such as this, so the data set, on which we train our network to output detections such as this. I can show you some more examples. Here again, you can see the road, you can see some cars detected. Yeah, some cars, the road, you can also see the lane markings, you can also see detected some cars here which are in the parking lot. Yeah. Another example here, with green, you can also see here it has detected, oh come on, it has detected, oh this is not, not really working. It has detected with green some traffic poles, yeah, traffic cones. And the main problem with this method is hard to determine why it fails in case it fails. So maybe we detect that there's an object in front of the road, even though there is nothing. This is a bit more challenging to determine why this happens. And there's another problem, which is this kind of neural network is susceptible that if you make small changes in the input, it has a big change in the output. Now, like you see here in this first image, you have some pedestrians here, yeah? And then you have the prediction, which says, okay, you can see the pedestrians with red. But if I add a certain noise pattern into the image, so the image below, you would not see this noise. You as a human can say, okay, this is almost the same image, but then the neural network with its prediction will detect no pedestrians, which is obviously very, very bad. So it's not easy to do such kind of noise, and it doesn't happen often, so it's a very particular case. But if we want to put something like this into a production car, we have to ensure that this never happens. We cannot lose lives because of stuff like this. Yeah? And now I will move on to the third possible method. And the third possible method relies on this 3D reconstruction which I showed you. Yeah? So you do the stuff in which you determine the shift of the objects in left and right, you construct the environment around it, and then you can determine which is the road. Advantages of this method is that you can determine what happened wrong in case you detect something which is not there, or in case you didn't detect an object which you should have detected. But the main problem with it is that the algorithm is very complex. Yeah? But still, it does work. So then, which of the three cases which I showed you would you use? Would you use the one in which you just detect the lane markings? Would you use the one with deep learning? Or would you use this one? And now the answer is we should use all three. And why is this? So by fusing information from several algorithms which aim to have the same result, we get a system which is robust, which is fail-safe. So in case one of the method fails, the other two will not fail. So the car will know what to do. It will know how to act, even in situations in which one of the algorithms is not good enough. So that's why the approach we have is a fusion between the three main ideas. We have classic lane detection, you have 3D measurements, so measurements constructed from the reconstruction of the 3D environment around the car, and from the deep learning-based semantic segmentation. And by a combination of these three, we aim to achieve a system which is very, very good. So what I want you to remember from this presentation is this fusion part, and that the fact that one algorithm is not good enough, and that automated cars or autonomous cars are very similar to us humans. So they have to sense the environment by means of sensors. So this would be radar, ultrasonic, camera, maybe also more expensive sensors which are lidar. Then it has to think, and this is by means of not just one single algorithm, but more than one algorithm, because one of them is not enough. And then it has to actually act. So it has to perform actions such as evasive steering, control the car, brake the car, accelerate the car, and so on. And now as a conclusion, so we at Bosch, and the general feeling of the autonomous driving community is that autonomous cars will become reality, but it's not an instant change. So it's not like I clap my hands and then we have an autonomous car. It's a step-by-step process. We started from partially automated cars, like those which can just control the steering or just control the pedals. We are moving towards cars which can control the entire car, but not in all conditions. And we aim to have a fully autonomous car. Why is this slide still up here? So we aim to have an autonomous car which works in all situations. Yeah? And this is, we have an engineering center in Cluj at Bosch in which we develop exactly this kind of algorithms as I've shown you. And we try to develop our competencies and become better at this, and strive towards the goal of having an autonomous car. Yeah. And I would like to thank you for your attention, and if you have questions, please.
Thank you, Lucian. We have 7 minutes for questions, so we can take a couple. Yeah, okay.
I expected there would be some questions on this, that's why I left a bit more time. Please.
Yeah, that's okay. What happens with the results of those algorithms? Are they displayed for the driver to take actions, or do you think or plan to actually stop the car or drive the car, steer the car?
No, so the idea is that the car will use the output of those algorithms to steer by itself. So the purpose is not to show it to the driver, the purpose is for the car to use the output of those algorithms and control the car. So the driver will only see the fact that the steering wheel is moving and the car is accelerating and braking. Of course, we can create very nice visualizations and we can show them to the driver, but they are not really helpful since he can't see the environment himself, so he can't see pedestrians, cars. Maybe at night it helps a bit, yeah, or in difficult situations, but the idea is we want the car to use them such that it controls the movement by itself.
Okay, what is more difficult to, I don't know, build the algorithm and the system that they showed us, or the interface to actually move or drive the car?
So both of them are really complex. So both of them are, I would say, are equally difficult. The team which I am working on is based on the first part, so detecting objects, and then we have an algorithm which performs decisions. So it sees some cars in front, maybe some pedestrians, and it has to decide what to do. So this must also be implemented. And then after decisions are taken, you pass these decisions to the steering part, which actually moves the car. But each component is very important. Yeah. And it's equally challenging to have a product which is very, very good in this fail-safe and is robust. So it's not like we are building a website and if it goes down, nothing happens. We are building cars which go on the road, and if they fail, someone dies, which is very bad, obviously. Yeah? So we must ensure that everything we do is very robust and it's fail-safe. That's why it's really, really challenging. Yeah? But we will have this. We partially have it today, and we will have it even better in the future. Yeah, with a level 5 car. Yeah.
So, question, how do you do the fusion of the algorithms, and what kind of measurement do you use for measuring the...
Yeah, so that is a very good question, but unfortunately this is confidential.
Okay.
So the important stuff is that we do the fusion. Exactly how it's done is property of the company. I cannot say. Yeah.
So in the part about the machine learning algorithm, you mentioned adversarial perturbation. I know it's used in an academic context to kind of mess with the network, see how bad you can make it screw up. What's the relevance in this context, though? Can it be used maliciously?
So this part about adversarial perturbation was done by a few colleagues, which are also at Bosch, I think from Germany, and they proved that if you can have access to the input, so you can have access to the images which the car sees, you can then create an algorithm which performs that particular noise which destroys the proper detection. So they did not investigate whether it's directly applicable to autonomous cars today, but they proved that if you have access to the input, then you can destroy the output. So it is a potential threat, yes.
Thank you.
Yes. Have you thought about ethics in case the car cannot stop? There are two types of decisions. Both are wrong, but yeah, killing a baby or an older woman, I don't know.
Yeah. So this is an age-old question in autonomous driving. So what do? Do you protect the driver which bought the car, or do you protect the people around the car? Now, obviously, this is a very sensitive subject, and we currently have no laws, or at least in my understanding, we have no laws which state which should you do. So there is no perfect answer to this. I expect that in the future we will have laws which will force the manufacturers of autonomous cars to take the ethical decision always. Yeah, but this first has to be determined by the laws of each state. So now each autonomous cars, or ones which we have in production, they try their best to just stop the car or evade some dangerous objects. Yeah, so we are not at the level with production cars that we can absolutely know all possible outcomes and then choose the best one. Yeah? We try to force ourselves to evade a collision. So this is what's currently done. But yes, I agree that the autonomous cars of the future, which we will have, should always take the ethical decision. Yeah.
Hello, so one question. I assume Bosch is working on providing a complete solution for autonomous driving. Can you provide us a timeline for highly autonomous or full autonomous?
Yeah, this is again an age-old question. So it's very hard to predict an exact timeline in which we will have, I think you are asking about the level 5 cars.
Level 4 and 5.
Level 4 and 5. So it's very difficult to say when we will have this, but as I said, it's a step-by-step process, and we are going towards it. Yeah. So we will definitely see, I mean, if you want a general, very general margin, we will see it in our lifetime. I do not want to be more precise than this. Yeah, but we will see it. Yeah.
Thank you.
For the vision and vision detecting, it's usually very important to have a well-calibrated system, and as you mentioned, robust. I would be curious to know if you have any monitoring or self-recalibration in time over the life of the product. So after the car has been on the road for 2 years, there are quite a lot of things that can happen, and the camera might get decalibrated and have wrong readings. How do you handle those situations?
So, again, I think this is confidential information, and I cannot tell you when we do the calibration or how we do the calibration, but the idea is that we do calibration. So, but exactly how and when we do it, I cannot say.
Hi, nice presentation. Yeah, liked it. And just asked myself, wondered if I may depart a little bit from the technical part and ask you about what your predictions are and your dreams. But before putting the question, I would like to construct a story a bit about our friend Kaiser Wilhelm.
Yeah.
That was presented with two choices. His horse that has a natural neural network that can be trained to go home in case he goes drunk or his driver goes drunk, and a simple mechanical car, which is very simple, and he looked at the two and chose what I think it was best at the time. So maybe we should apologize to Kaiser Wilhelm. I think he was a visionary. He chose better. And I want to ask you, what do you think, from your experience, looking at how your team work, if the same Kaiser Wilhelm would be raised from the dead, will he choose the Bosch car in the state it is now over his horse? Or should he wait a little bit more, and how much do you think? You should wait. Yeah.
The stuff that we are working on right now is aimed at production cars, and it's aimed at a level 3 system. Yeah? So this means that we aim to produce cars in which, in certain conditions, the car can drive autonomously, and the driver can, under certain conditions, take his eyes off the road. Yeah? This is the level that we want to put now into production cars. Now, I myself would trust such a car, while also knowing its limitations. So, you know that you cannot just put it onto autonomous driving mode and put yourself in the back seat, which would be level 5. Yeah? But it would really help for situations such as autonomous emergency braking. So in case you are looking at your phone or looking at your watch, it will brake. And these kind of systems are very good. So it's not really about the cars of the moment totally replacing the driver, but helping him in situations in which him by himself would produce an accident. So if you ask me personally, my car has autonomous emergency braking, and it did save my ass a couple of times. So I trust it. I try not to always rely on it. So I try not to let it break. I try to use it myself, but it will, and it will help me in the future, and it has helped me in the past. Yeah. So I would trust the systems that we build today. Yeah. Just as a side note, how do we know that our systems are very good? So we have a validation test in which we test each new system or each new release with 10,000 hours of driving. So this would mean that if I go into the car right now and I drive continuously for 1 year, the car will not perform an operation which would be bad for the driver or for the people around it. Yeah, so 10,000 hours. Does this answer your question?
So he will smile.
Yeah, I expect he will smile in this German way, in his German way, but he will smile, yeah. Yeah. Yeah.
So towards your goal of reaching a bigger level car, at the moment, do you rely only on pattern recognition methods, or do you consider learning from driver behavior or predicting driver behavior?
Again, unfortunately, I am sorry, I cannot answer this question due to confidential reasons, but what you say is a valid point. So a car which helps the driver would need to know the driver's habits. But if you want to replace the driver, then you don't have to use or know the driver's habits, because the driver's habits may be bad. So he may be an aggressive driver, or he may be a very slow driver or a very fast driver. So autonomous cars should be model drivers. So we do not want to bias them to be aggressive or to be passive. We want to make them as good as possible.
Perfect drivers. Okay, thank you, Lucian.
Thank you too.